Welcome everybody on Zoom. Welcome everybody in the lecture hall. Today we are going to continue speaking about data models and validation. So as a quick reminder, what we saw is 2 weeks ago, syntax. We looked at text files. These text files happens to be CSV or JSON or XML, but this was just text. And we saw that we can actually process this text to trees. And what we mean by trees is structures in the memory of your machine with memory pointers that organize the data as trees. And this is exactly what you've already seen in this Datenstrukturen und Algorithmen courses, right? Where you look at trees and lists and linked lists and all these structures. We literally build a tree in memory. Why do we do that? What would be an alternative to actually building the trees? Well, if you look on Stack Overflow, it's full of people who ask, how can I grab my XML or my JSON file to find what I'm looking for? This is a very, 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 very bad idea. Because when you just grab XML or JSON, first, you don't check whether the document is well formed, which already is very risky. And second, it's very inefficient, because you can grep for one thing. First, you're going to spend a lot of time trying to write your grep regular expression in order to find what you're looking for. That alone is not very productive. But on top of that, you will do it for one query, and then come the next query, and then you have to again grep through the file every time. But if you build in memory a structure like this with the pointers, you save yourself a lot of time for later, because then you can just forget about the original text version of JSON or XML, and you can just work in memory with your pointers. So already parsing, because this is what it's called, parsing the text that is JSON or XML or YAML or CSV well-formed into memory is already good for productivity and for performance. So this goes both for XML and JSON. This is what, in that sense, there is absolutely no difference in that respect between XML and JSON. Two words that you need to learn for today. There is a name for going up and going down here. When you take this and build the tree, this is called parsing, P-A-R-S-E, right? You parse into memory and build the structure. The other way around, who knows what it's called? If you take a tree in memory and serialize it back to the data lake or to text files. Oh, sorry, I said it, it was in the sentence. Yeah, okay. So serialize, that's called serializing. So you parse from text to the tree structure and you serialize back to text into memory. So typically when you parse, it's at the beginning of your query. You parse everything into memory. And at the end of your query, when you have produced the results as a tree in memory, you serialize it back to text in your data lake, and then you can export it and have other people download the output of your query. Okay. But now comes something more that we add, because this is only about well-formedness. Here, there is no notion of validation whatsoever. This is just well-formedness. And if it's well-formed, you can build the tree. Now we add a second layer on top of that, which is validation. It's yet another yes-no question that when a document is well-formed here, then you can also ask, is it valid or not valid? You need a schema for that. It depends on your schema, right? It might be valid against a schema and not valid against a different schema. So this depends on the schema. Well-formedness is universal. There is no additional info here, but here you need a schema. And the idea is that when you have a document like that, if you don't know about validation or anything, you would just parse this to a tree. Who sees a tree here? Almost all of you now, right? So you could build the tree in memory. In fact, you will if you parse that document into memory. However, you will quickly realize that you can do better than that. You can do better than that because if you just build a tree, you will notice a lot of repetition. For example, you will notice that every time you repeat foo and foo and foo and bar and you know, always the same things all over again, it takes space to do that when you build a tree. It actually takes space. So of course, there's techniques that are known as, for example, pooling the strings in order not to repeat them and so on. But nevertheless, it's not very efficient. And another aspect of that is that when you serialize that back, to how it is here, this takes space because every time you have foo, that eats up 5 bytes every time, right? You repeat the things all over again. So this is not efficient. And this is why when you recognize structures like this or patterns, you can take it to the next level in terms of productivity and performance by validating it. And then a whole realm of things become possible that you couldn't do just with well-formedness. And we'll look into all of these new things that you can do when you validate. And I cannot emphasize enough how important it is for querying and big data in general, understanding that it is absolutely central because this makes the difference between your query done in 1 hour or 1 week later. And that is a huge difference when you have to wait for a long time. Okay, so we will thus get into validation. And I will start by one aspect of validation that is super important, which is the types. And this will be a general introduction to types, not specifically tied to JSON or XML or any special schema language. I will try to give you a general introduction. But I need to motivate types first. I would like to motivate that. What types do we have in JSON just out of the blue, right? You take the JSON standards. What are the types that we have in there? On Zoom, maybe? Can you give me the types that are predefined in JSON? If you just work with what is available in the spec. Oh, wonderful. We have somebody on Zoom.
Yeah, it says string, bool, array, number, null, object.
Exactly. And that's the comprehensive list. There's just these 6, and that's it. Just these 6. How about XML? Let's focus on the atomic types. So there's 4 atomic types in JSON: string, number, boolean, null, plus the structured. What are the atomic types that you have in XML? On Zoom? Nobody? Yes, over there. Let's. I think it should be switched on. Oh, thank you.
So how about element, attribute?
Yes, element, attribute. And text. And text, right? Yeah. And text. So you're absolutely correct. So elements and attributes, let's put them aside because these are structured, right? This is when you have structure. But basically, text is the only thing we have in XML. There is no notion of number. There is no notion of Boolean. There is no notion of null or whatsoever. You just have text. You remember in the XML info set we saw yesterday, we have characters and text, and that's it. So you could argue that's string, right? So that's all you have. And you're absolutely correct. Indeed, you correctly remember we have elements, attributes, text, and with that, you can already cover probably 80% of the XML documents out there. All right. So just text. That's not great, right? Because if you look at typical good old databases like PostgreSQL and so on, you don't just have text, right? Or you don't just have string, number, Boolean, and null, right? Imagine PostgreSQL releasing, and the only 4 kinds of columns you can have is string, number, Boolean, null, right? Probably not a lot of people would be using this product. No, because in fact, in relational databases, you also have, first, you have plenty of types of numbers, right? You have doubles, floats, decimals, integers, and so on. You have dates and so on. So you have a rich type system, right? This is missing here. We don't have that in JSON or in XML, right? But this is data, so we need that. And in fact, this is part of the validation because when we validate and build the tree in memory, we will also use the opportunity to identify some of the types and actually enrich the whole ecosystem beyond just string, number, Boolean, null, and have like 20 plus atomic types in there. For whom does that make sense, the motivation? All right. And of course, as you can imagine, once you have something of a certain type, you save space again, because imagine that you have a date that is entered in text, in JSON or in XML as the year, the month, and the day, and maybe you also have hours, minutes, seconds, and so on. Takes a lot of space, right? Imagine all the bytes that you need in order to store that character by character. That's very expensive. And imagine you have 1 billion of them, super expensive. But if you, yes?
A question on Zoom.
Mm-hmm.
Do you consider elements as structured or atomic?
Structures. Yeah. So elements and attributes give the structure. How do I know that? Looking here. Basically, when I say atomic, I mean that these are the leaves of the tree. This is text. Elements are structured because they can have children, right? The same here. Objects are structured because they have children. Arrays are structured because they have children. And the leaves are all my atomic values, right? So this is why in XML, there's just text. You could argue also that the value of an attribute can also be, but it's still just text, right? It's not called text in the XML model, but it's also a string, right? Wonderful, okay. And I'm sure if you ask, then a lot of other people wonder, right? Okay, so elements and atomics and objects and arrays are structured. Okay, so the types, if you store dates in JSON or XML, it's very, very space consuming because you need to write it down character by character. And adds to that it's a big mess because many people might use different standards or different ways of actually storing the strings of the dates. But if you have a specific point in time and you know it's a date, you can store it instead as just a long, right? Just, you know, one of the standards is the number of milliseconds elapsed since the 1st of January, 1970, right? So if you just store a long, you are looking at 64 bits, right? Just 8 bytes. And 8 bytes is already probably less than half, maybe even a third of the space that the text representing the date was taking. For whom is that clear? All right, so this is yet another motivation that having types and identifying types is going to save us space. And who says saving space means less time to read from disk, means faster query execution, and means you can squeeze even more data into your memory. And if you manage to query everything in memory, then it's super fast. So maybe you could squeeze, I don't know, 1 gigabyte. And now using that, you can squeeze 5 gigabytes or maybe even 10 gigabytes of data in the same amount of memory. All right. So I have good news for you. And the good news is that if you look at all the technologies, there are so many of them, we will not be able to cover them, but they have more or less the same ideas. It's the same ideas everywhere. Be it even object-oriented programming, right? So Java, Python. I put a lot of scary things in there, but we look into them. The protocol buffers that one of you mentioned yesterday, Avro and Parquet, which are formats, binary formats for data. JDM, that's the JSONic data model we'll study later for JSON. PSVI is a scary term that just means when you have validated XML, what you have in memory. But don't be scared like that. What I'm saying on that slide is simple. No matter what technology you pick, it will more or less follow the same patterns. In particular, almost all of these technologies, if not all of them, distinguish between the notion of an atomic type and a structured type. Right? Like element attributes on one side, text on the other, object and arrays on the one side, and string, number, Boolean, null on the other side. The same goes in Java. In Java, you have the notion of objects, that would be the structured types. Then you have the primitive types, right? Int, short, byte, and so on, all of these primitive types. String in Java turns out to be a structured type, right? It's just, let's say, one of the peculiarities of Java. But you have this distinction in Java between the two kinds of types as well. In Python, you have dictionaries, dicts, and you have lists as well. These are the structured types, and you have the atomic types as well. Okay, so you have this distinction. Second, you have the same categories of atomic types. We'll do a quick survey. They don't exactly have the same types, but more or less the categories are the same. So you just need a general understanding of what to expect. Then the structured types are very often of two kinds, lists and maps, and that's pretty much all you have. Maybe sets and bags in some languages that push it to the next level, but typically you have lists and maps. And finally, when you have sequence types, meaning every time you have a list or a collection of things, you can restrict the cardinality, 1, 0, just one, any number, and so on. And everything I said is totally independent on the technology. This is general. No matter what technology you pick, it's highly likely that it's going to follow this model, right? So I have a few slides to just repeat what I'm saying, that in most technologies, you distinguish between the atomic types that would be at the leaves of the tree. These are the leaves of your tree representation. And the structured types would be the non-terminal nodes, like the nodes that are not leaves, right? Objects, arrays, elements, attributes, objects in Java, and so on. For whom is this distinction clear now? Okay. This distinction is the same one that is used to characterize the first normal form. When you say a relational table is in the first normal form, if all the values are atomic, it's the same thing here, the same atomic. Right. In the first normal form, you would only allow the cells to contain atomic values and no structured values. So you cannot have objects or attributes or elements or arrays or anything that is not atomic. Okay, let's move on. So now we'll go through a catalog of atomic types, but in a way that you will see is actually generic. So first, well, you're computer scientists, so I'm not going to spend a lot of time on this, right? You know that a string is a sequence of characters that you can represent with just bytes in memory. The only important thing, but again, you probably heard it a lot, is to try to use for internationalization to stick to Unicode and UTF-8 for the representation so that you're fully generic. But when you reason at the level of querying the data, you don't even care if it was UTF-8 or UTF-16 or ASCII or whatever. You reason already at the level of the Unicode, the level of the actual characters. All right. Okay, so yeah, I don't think I need to say much more about strings. Then you have the numbers. So you know the good old types that you have in almost any language. You at least have these basic integer types. So in Java, they are called byte, short, int, and long, right? On 8, on 16, on 32, and on 64 bits. And of course, the names might differ. So this is where you need a lot of flexibility, right? Because some of the languages might call them differently, but nevertheless, this distinction, these types are almost always here. Okay, next, what you will find is a type system beyond that. So here it's actually restrictive, right? If you're limiting yourself, for example, to 32 bits or 64 bits gives you a bit more freedom, but still that's 2 to the power of 64. So that's 1 quintillion. You cannot go beyond 1 quintillion, right? If you want to go beyond that, then you have types that basically reason on the, you know, how you write a number in base 10. And you can define types where you say, this is the precision I want. For example, I want, I don't know, 40 digits of precision. So it's the total number of significant digits I have on either side of the decimal period. And the second parameter that I can give to my type is the scale. It's the number of digits that I have after the decimal period. So you define a maximum precision and a scale here. The third parameter is implicit. That's just the precision minus the scale gives you the number of digits that you have on the left, right? But it would be redundant to specify it. And basically, this is called fixed point decimals in the sense that you have all your digits and the decimal period is implicitly here at that position given by the scale, right? So this is fixed point. And there's a lot of research and in mathematical software also where they typically have that because they need a lot of precision for physicists also. This is beyond just this. You could also use fixed point on just 64 bits, right? If your number of digits is small enough, you could abuse these types here. But if you go beyond, then you need these new sets of types. Okay. In SQL, PostgreSQL is called numeric, right? And then you pass the precision and the scale in order to save it. Typically, the systems are a bit limited. For example, I think in the case of Spark SQL, which we will see in a few weeks, the precision can be at most 38, I think, and the scale at most 19. Anything beyond that would not be supported. Okay. And then you had a beautiful extension that was made actually with XML and JSON is that there is no more limitation on the precision. And in XML and JSON, you can have, even if you want 1,000 digits, you can have 1,000 digits. I'm not going to say it's fast, but you can have it. We have a question over there. Maybe we can throw the catch box.
Yeah, I wanted to ask, why is fixed point more precise than floating point?
Oh, so let me talk about floating point then, and then I address that, because I also include floating point. But I can answer your question directly, in fact. Look at these standards, float and double for floating point. You can see that in the case of float, which is the 32-bit version of floating point numbers, that gives you roughly 7 digits. It's not a lot, right? The precision, just have 7 decimal digits. If you go to 64 bits, that gives you 15 digits. If you want a precision beyond that, let's say you want 20 or 30 digits, this doesn't work anymore, right? Because it's going to forget anything that is beyond after the decimal periods. This is why in mathematical software, if you want more than that precision, they will not just use float and doubles, they will use specialized libraries to support that kind of things that goes beyond. In Java, who knows big integer and big decimal? This is what it is. Big decimal and big integer is exactly this, or this, right? This would be in Java, float and double. So you need to distinguish between these two kinds where this is highly optimized. It's a standard that's super efficient at the CPU level, but you are limited in the digits. However, what it gives you is this amazing interval of powers of 10 that you can have, right? Here you can have numbers that go all the way to 10 to the power of 300, right? If you try to do it here, that would be very inefficient, because then you need to go all the way, with 300 zeros here. So this is also, just to contrast the two, that each has their own advantages and inconvenience drawbacks. Do we have on Zoom? You have this contrast between, on the one hand, this arbitrary precision decimals and integers. How do you make it integers? You just say the scale is 0, right? So integer is just a special case of that where the scale is 0. So either this, big integer, big decimal in Java, or float and double, which is the IEEE 754 standard. I have no idea why I know that by heart, but this is the name of the standard. Yeah, even in Python, I think you also have that. For some reason, Python calls that float, I think. Is that correct? I think it's called float and double in Java. Okay. So this is for the numbers. So you see that JSON just has numbers, but in a type system, you want more distinction between all the different kinds of numbers that there are out there. Okay, Booleans, again, you're computer scientists, I'm not gonna say much. There is true, there is false, there is not so much more to say than that, right? Except maybe that unlike SQL, in the realm of big data, we don't really do 3-valued logic. So typically it's just true and false when we talk about Booleans. Okay, so yeah. Then let's look at something that is very often underestimated, especially when people build a new products and they add types. The ones they will forget are the dates and times. The problem is, if you're a company, you will need dates and times. So that's the paradox of things, is that in the industry, they are all over the place. But when you develop the product, these are the ones you forget. But anyway, in XML and JSON, and we have this kind of types. In many languages, there's also libraries, like in Java, but it keeps evolving, but there are also libraries for that. Okay, so the dates in the Gregorian calendar, because there's actually plenty more calendars out there, and some systems even support multiple calendars. But the most widely used in the world is the Gregorian calendar, where you have a year, you have a month, and you have a day. Now, oh, I thought I had, maybe it's not I thought I had added slides that I'm surprised not to see. This is why I was wondering. Okay, so I'll give you the literals later. Okay, then you have the types, the times. So the times give you hours, minutes, and seconds separated by a colon. And many systems also go to a precision of millisecond or microsecond, right? And that's the case typically in the types that we will study for JSON and XML. And finally, you have timestamps that have the whole thing with the year, the month, the day, the hours, the minutes, the seconds. Typically, you can encode that efficiently in memory, just storing it as a single long. Okay. So these are the dates and times. Typically, what I didn't say here, I actually had added the slides that I don't know why they disappeared. You also have time zones. You can have support for time zones. For example, this could be UTC or Zurich time or Pacific time and so on. And this is something you can also add to a type or to a timestamp that is additional information, right? Okay, so these are dates and times. Then we have intervals. And intervals are a bit tricky because there is a bit of, let's say, a wall in between. And that wall is between months and days. So you can have time intervals with years and months that is unambiguous, 2 years and 4 months, for example. You can have intervals with days, hours, minutes and seconds, like 3 hours and 14 minutes, right? What is tricky is when you have months and days. If I tell you 1 month and 2 days, that's ambiguous because a month could have 30 days, 31 days, 28 days. So this is why to be a bit careful when you cross that border between month and day, right? But basically you can define intervals in that way. Okay. Next, we have binaries. How do you store binary values? This is also something you can do in PostgreSQL, right? You can store binary values. There are 2 kinds, if I can say a few words about that. There are mainly 2 kinds of literals for binaries. You can have them in base 16 with the digits from 0 to 9 and from A to F, right? So in base 16. The other one is in base 64. Who knows base 64? Right, so it's very smart actually. It's more efficient than base 16. In base 64, as the name indicates, you encode that with 64 digits. You have all the letters lowercase, all the letters uppercase. We are at 52. All the 10 decimal digits brings us at 62. And the 2 last ones, I think, is the slash and the plus. And that gives you 64, base 64 digits. And then what you do is that you encode the binary. You basically take 6 bits at a time. Every time you have 6 bits, that's a digit in base 64, and you encode it with one of these 64 digits. All right, so this is base 64. You will find that on the web a lot, right? You can embed binary things on an HTML page or even in an XML or JSON document and put pictures or plenty of things in there. All right. And finally, null, which is a value that we treat outside of things in JSON because it's a special value, the null literal. The interpretation varies a lot. Some products will tell you null is equivalent to the absence of value. So if you have foobar : null in JSON, it's the same thing as not having it at all. Some other products will make a difference. If it's not there, if it's null, it's not the same thing. So you have to be a bit careful about the semantics. In XML, null exists as well. It's just that it's not with a literal null, it's with a specific attribute, but I'm not going to annoy you too much with that, right? But basically, if you look at all this menu of atomic types, no matter what technology you look at, it will have in one way or the other these types, okay? What's important is that since we are dealing with text, originally it comes from XML and JSON, and when you parse it to memory, you might still have text, so a sequence of characters. You need to be aware that what's going on here is that there is some mapping or some it's not a bijection. This is why it's tricky. It's not a bijection, it's more of a correspondence between what we call the lexical space and the value space. What is the lexical space? That's the text that you see in the XML or JSON document. For example, for a date, you might see 2022-1 10-26, which would be today's date. That's the lexical, that's a literal, it's the lexical value. Then you have the value space, which is the mathematical value. For example, when you have the integer, in that case, the integer 1, its lexical representation or its literal, it's equivalent to say it one way or the other, 1 or 0, 1, it's all the same. Mathematically, this represents the concept of oneness, right? Here, there's the concept of the number 4, where you have either 4 or 4E00, or in base 2, 100B, and so on. These are all literals or lexical representations that are all equivalent and pointing to the concept of the number 4, okay? And then, of course, when you parse, you go from the lexical space to the value space. I should even have said not just parse, but also validate, because if you just parse, then you don't actually have the types yet. And when you serialize, you take the value space and convert it back to a lexical value. So of course, since it's ambiguous, when you serialize back, you need some sort of canonical convention. For example, you need to say that if you want to serialize 4, then just put the character 4 and that's it. I don't know many serializers or products that would serialize 4 as plus 4E00, right? So there is a bit of a preference for a canonical way of serializing back the value. Okay. Now, many products, not all though, some products do not have that. Many products have the concept of supertypes and subtypes. If you know object-oriented programming, you already know what that is. But what this means from the perspective of data or big data is a bit different from object-oriented programming. Because when you look at types and supertypes for data, it's really looking at the value spaces. What are all the values in that type versus all the values in the other types? And if you have a set inclusion, meaning that every value valid against the subtype is also valid against the supertype, then we are in a supertype-subtype relationship. Right? An example of that is long and int. Int is a subtype of long, because any integer you can encode with 32 bits is also an integer you can encode with 64 bits, right? Another example is that infinite precision integers, that's a subtype of infinite precision decimals, right? It's just a scale of 0. And so on, right? You have this relationship between the spaces. Okay. Now, the structured types. It's also the same almost everywhere. XML is a bit special, but nevertheless, it still kind of fits in there. I said that in many of these systems, you have 2 structured types that are all over the place, which are basically lists and maps. Right, these 2. Maps are basically JSON objects. You also find map structures when you look at XML attributes within the same element. You can also view that as a map. And we'll see later when we look at data frames, so next week, and then we'll see them in Apache Spark, a data frame struct is also a map, right? We'll see later. Then if you look at lists, JSON arrays are lists. XML elements can also be seen as lists because it's order sensitive. Within an element just has children that are other elements and text. And as we said yesterday, I think somebody asked the question, it is order sensitive. So this is why I'm putting it as a list right here, right? And finally, we'll see when we look at data frames that arrays in data frames also are lists, okay? All right. And finally, I think that was my final point for the general approach to types. If you look at the notion of restricting the cardinality of a sequence, for example, do you want an array to have exactly one value or 0 or 1 value or at least 1 value or any number of values, right? The same applies to a collection of objects, right, that you might restrict. So this is called the cardinality, right? And it turns out that here too, many technologies have exactly these 4 categories out there of cardinalities. The first one is exactly 1, right? The second one is 0 or 1, and this one is associated often with a question mark. That shouldn't surprise you because this is actually like in regular expressions. So if you know regular expressions, then that will be very easy for you to remember, right? So you can have 0 or 1. If you take a programming language like Java, it actually does have 0 or 1 semantics everywhere. Because in Java, either you have one single value, which is an instance of your static type, or it's a null. So that's a 0 or 1, if you consider null as not having any value, right? So 0 or 1 in Java and many programming languages, that's the way it works. Then you have 0 or more, which is the star, again, in regex, regular expressions, that's exactly the symbol as well. And 1 or more is a plus, that's also like in regular expressions, right? So that should make it easy to remember. And some of the languages do not use the star, the question mark, and the plus, but instead they use keywords. So for example, if it's exactly 1, they'd say required. For 0 or more, they'd say repeated, and 0 or 1, they'd say optional. I think I had the protocol buffers in mind with that latest column. This is how protocol buffers actually do it. Okay. And now I have this summary table. It's not complete, right? But it actually has a lot of them. This was actually a request of one of your colleagues a few years ago who asked, like, can I have an overview of all the types and so on? But the first thing I want to say here is don't be scared. This is not something to be scared of. This is something to be happy about. Because what is the message on that slide? The message is it's the same everywhere. You might have different names, might be called differently, but you know, it's like in Switzerland, right? You might use a different word if you're in the canton of Zurich or Basel or in Valais. But in the end, we just call the same things, even with these different words. So the great news here is that if you learn one of them, then you've learned them all, right? Because imagine you see, for example, that you have integers in JSON or JSONic, which we'll see shortly. Integer means arbitrary precision integer. Imagine now you're learning Python. Easy, look up the documentation, then you just realize that's called int. And that's it. So you just remember now it's called int in Python, but it's the same type. The same for double. You know that in Java, in JSON, in XML, also in Spark SQL, double type, PostgreSQL calls it double precision. And you look at it up in Python, it's called float, but who cares that it's called float? All you need to know is this is a double precision IE 754 encoding, right? This is my type. Some other examples were interesting things. For example, the longs, you see it's called long here. In JSON schema, that would be an integer and you add a range. In XML, it's called long. In Spark SQL, it's called long. In PostgreSQL, it's called bigint. But again, nothing to be scared of. It's only a matter of looking it up in the documentation and finding out how it's called. I wanted to say a few words on decimal in integer, because if you look at Spark SQL and PostgreSQL, it's something that I mentioned earlier. You actually have limits. In Spark SQL, you cannot be beyond 38 of precision and 19 of scale. In PostgreSQL, I think it's limited too. I can't remember the exact limits, but I think it has limits as well. What's the really nice thing about XML and JSON is that in XML and JSON, you don't have this limitation, at least in the standard. A particular implementation might say, okay, we don't support beyond that. But in general, XML and JSON as a standard have absolutely no limitation as for the size and precision and scale of integers and decimals. And you see at the end, you have the structured types over there. Maybe I can unhide using the trick that I learned from you. Click on the chat, click again here, close the chat, and that disappears there. So you see that the notion of object and array is also universal, except in XML, but that we knew, right? That in XML, there's no objects and arrays. So in Spark SQL, objects are called structs. In Python, they are called dict. Array in JSON is called array type in Spark SQL. In PostgreSQL, there is also a notation for arrays that you can use. I put the square brackets in there. And in Python, it's called list. Okay. For whom does that make sense? Right. So it's not everything. There are more types in there. But what I'm saying is that if you have general knowledge about these categories and the kind of things to expect, then maybe there will be a new technology that will appear in 5 years, or maybe you go to a new employer in 2 years after you graduate and they say, okay, we're going to work with that technology. all you need to do is look up the documentation, figure out how the types are called, but it's highly likely that it's more or less going to be the same, right? So you really need this to zoom out and see the big picture here, and not let yourself be scared of that. All right. For the purpose of this course, we'll tend to use the types under JSONic and XML schema, but you might have noticed these are the same. There's actually no difference. You see just there is a namespace in the case of XML schema, but these are the same ones. So it's just for pedagogical purposes that we stick to a convention. All right. Now, checking the time. Still have a few minutes. So now that we have this overview of types and we saw the general things to expect in many technologies, let's look at specific technologies. So we look at JSON, I will tell you about this, JSON schema and XML schema as examples. And at the end, I also talk to you about Parquet and protocol buffers, and all these technologies, but again, with the idea that it's really all the same. So what is JSON? JSON was actually, it was co-designed with colleagues of mine and myself. Mostly, so what I had in mind is a teaching environment. How do you teach validation and find a pedagogical way to explain it? The other goals, and especially pushed by my colleagues, were that it should be simple and standard, meaning that it's learning a lot from the past, in particular from XML schema. So I'm going to show you how to design JSON schema, and hopefully you will find it very simple, and that will help you get the idea of what it means to validate. So let's start with a simple example. Every time when we try to validate data, I will put on one part of the slide the actual data we want to validate. The fancy word for that is instance. We want to validate an instance. So this is why I put instance over there with file.json. If you store it in some, that would be the name of the file. And on the other part of the slide, I put the schema itself, which is also stored in some file, right? So we have the instance, which is the data we want to validate, and which is the schema that gives us the information about what structure we want to find in there. Does anybody notice anything with the schema? Something that catches your eye? Yes, over there maybe. It is also JSON, exactly. The schema is also JSON. And that is actually on purpose, right? The same goes with JSON schema. A JSON schema is also going to be a JSON object. And the same in XML. In XML schema, an XML schema is also an XML element. So this is also something you find very often. It's not always the case, right? For protocol buffers, for example, the schemas have their own definition. The same goes for data frames in Spark SQL and so on, right? But in the case of JSON and XML, you typically have the same syntax, which is JSON. Now, what do we have here? You notice that the pattern is similar. What is the only difference between the two is just I put just the type here, string. Where does string come from? That comes from my list right there. So I'm saying we expect an object that has a key called last, and the value associated with that should be a string. Is that a string? Yes, this is a string. So this is valid against this schema. All right, and it's that simple. Now, we can have more, right? So we can have last and first. So here we have last, Einstein, first, Albert, and I can have just last, which must be a string, and first, that must be a string. And you see, so this is the way that JSON was designed in this compact syntax is that there is really something very similar in the way that the document looks and the schema looks, which makes it very intuitive. All right. For whom does that make sense? Right? This is relatively easy, right? Now, by default, if you just specify, oh, it's almost the end, so I will stop here. Optional is the default, meaning that every time you define something here, it's okay if it's missing, right? There is a way we will see later to force it to be here, but it's not, it's okay to have either first or last or both missing in the schema. All right, I see, so yes, I will answer your question and then we will stop. There is no order. So in JSON objects, it's a map and there is no order in the maps, but I will say a few words about that next week about the order, because in practice, there might be some, but I will come back to that. So thank you very much, everybody. And I will see you next week, Tuesday at 2 p.m. for the continuation. Thank you.